So
Okay,
you
thank you.
may start.
Yeah.
Thank you.
Hello everyone. I'm Rahul Raman. So today I'm presenting a research titled "A Comparative Study on Language Models for the Kannada Language." This work was jointly done by Danish Abadullah, myself, Hriday Karan Shetty, and Dr. Mamta HR from PES University. So with the advent of the BERT, there's been a rise in popularity in using these language models for multiple downstream tasks such as news classification, word similarity, or even neural machine translation up to an extent. And it has been on multiple languages like many European languages, English languages, or even in Indian languages such as the Hindi. I guess everyone would have heard about that. But then, despite this popularity, there hasn't been much inclined research towards the Indo-Dravidian languages. So the main reason for that is because of the scarcity of the data. And for that very reason, we have actually taken up the challenge and decided to take the language as Kannada, which is one of the four Indo-Dravidian languages, and is considered to be morphologically rich in nature. So for instance, so when do we say language is morphologically rich? So given a word, you have multiple suffixes for it. I mean, just add some suffix and you have multiple inflections of that word. So just for an instance, if you take the word money, which is house in Kannada, so if you just add galu, which mane galu, and if you have ali, it becomes mane ali, and if you have avuru, it becomes mane avuru, which respectively stands for houses, in the house, and household. So this is just an example of, this is just a few suffixes I've taken and added to this. So just for an imagination of how many suffixes can be there. So there's actually twice the amount, the vocabulary size is twice the amount of, in English set. So it is about 52 or 53, I guess, the phonetic characters. And there was just an example for house, which is considered to be a bit more simpler terms, such that I can put in a slide to just show you the few words over there. So considering all these things, so the whole insight of a paper is first to give an effect of the vocabulary size. And second is to do a comparison between different language models, starting from the very basic shallow neural networks, which were context independent. So for example, the fast text models, which were inherently CBOW and SkipGram models, and moving up all the way up to the recent research, which is like 2018 BERT. So BERT is like a deep neural network, but then we have decided to train it in two alternate methods, which is in Roberta and Electra. So for training this data, we have used this publicly available data set, INDIC and LP. They have publicly made it available. And speaking about the data set, it's actually domain specific, mainly because it comprises of like, Bible translations or our prime minister speeches translated, and probably a few more from the website scraping. So mainly due to this reason itself, there aren't many people who would like to, go to this Indo-Dravidian part, and they just stick with the, Indo-Aryan languages such as Hindi. But we just decided to, have a research upon this area. So moving on to our first insight, which is the effect of vocabulary. So in general, like when you say we do any task, we like any natural language task, like be like, neural machine translation or anything, we always consider a bigger vocabulary size because we don't want any out of vocabulary tokens and all, and that might not give us a better results later on. But then when we did this for a morphologically rich language, it turned out to be there was a slight issue in it. So to demonstrate the issue of the effect of vocabulary, the most prominent task to do would probably be word similarity. So for word similarity, what we have done is that we have taken this word man, just for an instance, we have taken this man, which is Manusya in Kannada. We have fed it into a model with a size 16K vocabulary. So the top three predicted words are Kumaranu, which means son in Kannada, Strike, which means female in Kannada, and Huduga, which means boy in Kannada. So if you see the predictions, it's actually more or less like the synonyms or used in a similar context of the word. But then now when we look at the 32K vocabulary size, the words you get is Manusyana, which is mankind, Manusyanike, which is for the mankind, and Manusya Ninda, which is by man. Now, if you just observe it, you can see it's basically the same word Manusya with added some prefix and suffix. So which is basically like the inflections of the word. So that was something we found useful. That is, in richer languages, if you just put some large vocabulary size, you might probably just be filling your whole vocabulary, to clutter your whole vocabulary with, just the inflections of the same word, which are commonly used, you can say. Now, moving on, now we just shifted up and we are going to the, the deep neural networks. So initially we were planning to go with the BERT model, but it turned out that the BERT model had been undertrained by a research claim by Roberta paper. So what's the difference between Roberta and BERT? So BERT is trained basically on next sentence prediction along with static masking, while Roberta does a dynamic masking. So the very reason of why we chose Roberta over BERT or for pre-training phase, because that's the only difference. Like Roberta and BERT use the same model, which is BERT. The only difference is how they pre-train it during the pre-training phase. So Roberta, what they do is that they claim that NSP does more harm than any good to the model. And the second reason of why we don't use that is because the sentences either have to be long enough such that you can find an appropriate partition and feed it as a generated data for next sentence prediction, or you should have well documented sentences such that you can say sentence A then sentence B and you can have a prediction is sentence B after sentence A. But unfortunately, our data set, we didn't scrape it. We have actually taken the publicly available one and it's shuffled. So we weren't quite sure about using this next sentence space. But it turned out since it's not doing any good, so we thought, why to even try about that? And the second reason is that in dynamic masking, the same sequence is actually masked differently over various iterations, over many iterations. So it's like as if you're feeding a new sentence over the next iteration. So in the first epoch, you can say in the example you can see, so E1, E2, E3 are just the embeddings. Let's say that's how the tokens are tokenized and get the embeddings over there. So in the first iteration, you can see the first word is masked and the second, third word are shown. So you have to predict the first word. The second sentence is the first word is there, second word is masked, and third word is present. So you have to present second, so on and so forth. So that's dynamic masking there. So we thought that would be one more useful thing. And the third useful thing, which we plan to change a bit, was if you see any paper, we always say we use word level tokenizer or sub-word level tokenizer. But our intention was that if we use something like that, we should have a larger vocabulary size to fit the whole complex, morphologically rich language. But if we do that from a previous insight, as we told, it's just cluttered with the inflections. So how do we solve this? We actually do a byte level BP. So what does byte level BP means? So we actually convert our whole data set into byte level, 256 byte level character set. No, by 256 byte level set, sorry, that's a byte level set. And once you are converted that, then you use our regular BP encoding algorithm to find the sub. So basically we're not doing sub word, but we're doing sub byte characters. Okay. So you're doing a sub byte and you're finding it. So this was, if you ask me where this was used, it was actually used in GPT-2 transformers. So that's where we got our idea from. Why not use it? And even if you read the paper, they've used it for Chinese and Japanese languages, which are way more morphologically rich than our languages. So yeah, so we thought that that could be good and useful for our planning. Now, moving on to the next model we used, which was Electra. To be honest, this was a very experimental model because this released during the early 2020s, I guess during March or April. So it was relatively new and it was again released by Google and it was still, the GitHub was still under development. So the overall idea was, it's a very intriguing idea, that is, as in like when you compare a BERT or a Roberta model, they're actually generator model. That is, you give a masked sentence, you ask during the pre-training phase, you give a masked sentence, you ask you to predict what that masked word can be. But then Electra is actually a discriminator. So how does this actually happen? So in an overall view, this is a basic GAN structure. So in the generator side, we can have just like a BERT language model or anything. A small BERT language model should be sufficient. The reason is that you have to predict. So the BERT, the aim of the generator is to predict the mask token. So once you predict that mask token, you actually feed it into Electra, the whole sentence plus the mask token. Now the Electra, which is the discriminator, has to decide whether it's from the original sentence or was it predicted by the generator. So original or replace, that's the option there. So this was the reason behind this intuitive idea was, I guess, mainly due to the fact that during a pre-training phase, you use a masked language model, that is, you use mask token. But then during your fine-tuning phase, let's say you're doing news classification, let's say you're doing some sort of word analogy, you never have this token mask. Okay. So the question, so it has been, I'm not sure if it's been proved scientifically, but I think it's an experimental proof that you sort of ambiguate it and there's a sort of confusion during the fine-tuning time and it takes more time to train. So actually in the paper, they specified even better that as in when they do it in this way, they actually, even with a smaller model, which is of 14 million parameters, they were actually able to defeat the original BERT itself. So I guess no, actually that was BERT Electra large, which is 128 million. So that's still 4 times smaller and it was still able to defeat. So the models we have used, so in Roberta case, we have actually, there was one thing I've missed actually, forgot to point it out. That is in Roberta, which is model parameters, as many people have been asking, what is your configurations you use? So we actually use the distal BERT configuration for Roberta. pardon me, because I'm just going back to slide. We use a distill bird configuration, so which is basically 40% of bird base size, and it retains 97% of accuracy, and yeah, it's 60% faster due to that size reduction. So the question could be, why do you do that? One major reason is because if you see anyone using bird-based models or anything, they actually use it on multiple languages. But then we are just using it on a single language and don't have sufficient data to train such a large model. And the second reason is that, yeah, we don't have the computational resource either. So yeah, we had to stick with a smaller model. So the model for Roberta we have used was an 85 million parameter approximately. And the Electra one was approximately 14 to 15 million in that range. I guess towards 15 because it was 14.9 something. So yes, towards 15 million parameters. Now moving on to results. The one downstream task which we decided to do was the evaluation on the Indic NLP news article classification. So this was a very standardized test among all the Indians, among the Indian research work. So what the classes are: entertainment, lifestyle, and sports. So we just tested on that all our models, like even our some small models like FastText and all the way up to Robert and Electra models. So the FastText model and all didn't perform quite well to the state of the art, probably by 2% the marginal loss. So the FastText WC is actually the original Facebook one. So they've trained it on 157 different languages, and they were still able to perform quite exceedingly well. Okay. And the second one is this Indic NLP, which was 97.2%. That's also another work. They used FastText, but they only trained it on 13 Indian languages specifically. Now comes our model, Roberta. It was able to perform it was able to get an accuracy of 97.37%. So the best part is that we are actually only trained it for probably one epoch, at max two, I think. But the whole part is that even by just training 1 to 2 epochs, we were actually able to get we were able to be on par with the current state of our models. And when coming to Electra, even though it's a 14 million parameter model, we were still able to quite outperform by showing a 98.53%. So yeah, the paper claims of Electra was actually quite neat, and that's actually true. And finally, INLTK model, that was a transformer Excel model that had, I guess, 283 million parameters. We are 20 times smaller, and we still had I guess, 0.3% as a marginal difference. So I thought that was, a compact model able to perform was quite good. But yeah, at the same time, a contrastive talk could be that, hey, they use multiple languages, you're only doing one single. Yeah, it's a point, but yeah, we just go with it. So now finally coming to the related work. So the 4 papers I mentioned below, they are actually the same as what I mentioned during the table section. So yeah, all of them actually use the more or less similar data set, except for the last one, enriching word vectors with subword information. That is the original FastText and the Wikipedia crawl, and they're used for that. The other 3 I've just used the same data set, which is our Indic NLP data set. The only thing they vary is one of them use FastText, one of them use Transformer Excel. So actually 2 of them use FastText and one of them use Transformer Excel. And yeah, finally, our paper is comparative study on language models for Kannada language, and that's the QR code. We have publicly made it available in Hugging Face, such that and it's only the Electra model, by the way. So if anyone is interested in doing any downstream task, or do it for another benchmark, because I guess this benchmark was pretty simple in my opinion, that everyone was able to perform quite well. So yeah, if anyone finds a new thing and wants to put a challenge, yeah, feel free to take it. And yeah, in future, we are actually planning to put our Roberta model after we train it properly. And thank you. And I guess now I'm open to any questions.